Hello, welcome to the third lecture of this course. In the last lecture, we discussed a generic two-level system and without any external driving. In this lecture, let us see how a two-level system behaves under the influence of time-dependent driving. So let us begin. In the last class, we established that the Hamiltonian of a generic two-level system will now not say TLS is given by, or we can actually express it or put in this particular form, say H is equal to epsilon dot sigma, where sigma is the Pauli vector, and this is a time independent Hamiltonian, and this is without any external drive. Okay, and from our analysis we learned that this Pauli vector, this sigma, precesses around this epsilon vector, and we plotted it. Actually, we can plot the expectation value of sigma, and it turns out that it precesses around this vector epsilon with precession frequency twice epsilon by h cross, mod of twice epsilon by h cross. So in fact, the dynamics of a two-level system when it is not externally derived can be discussed or described by evolution of these Pauli matrices. So this quantity, expectation value of sigma, this quantity is known as the so-called block vector. So once we know this block vector, effectively we know everything about a two-level system. Now let us see what happens if a two-level system is put under driving. So two-level system under time dependent driving. So this is what we are going to discuss today in this class, and you will see very nice physics will come out because of that. So what we will do, we'll begin with a Hamiltonian which is already diagonalized. So let us say our Hamiltonian is of this form, say epsilon sigma z. Okay, now at the moment we are not applying any driving, by the way, and this sigma z is, you know, Pauli z component of the Pauli matrix. So it is 1 0 0 minus 1. So in matrix form, this Hamiltonian is basically have epsilon 0 0 minus epsilon. So this, or we are having a configuration like this where the ground state has, say, energy is represented by energy minus epsilon and plus epsilon. So energy gap is twice epsilon. Okay, now let us drive this two-level system externally. That means suppose we apply some kind of a time dependent or a pulse, suppose we are throwing at this two-level system, then what happens in that case? So in that case we can have it like this, sigma z plus, now you are applying a time dependent driving. Suppose we are applying a cos sinusoidal wave like this, cos omega t, and so it has this driving has frequency, say omega, this is the driving frequency, and you need to have, it has to has the dimension of energy. So let us say it has energy s cross omega, where omega is the so-called driving amplitude, and it has to be a 2 by 2 Hamiltonian again. So let us say I have sigma z. But if I have this kind of driving, because sigma z, as you see here, it has these diagonal elements only, so 1 and -1, that means it can only affect these energy levels, and by applying this driving we are not going to get any interesting physics as such, because what it basically means that these energy levels would be shifted upward and downward like this. Nothing, no kind of, no transition is going to take place. So if we really want to have nice physics out of it, so what we will do, we'll say we'll apply a drive like this, say it would be sigma x or sigma y, because we know that if I have sigma x and this Pauli matrix is basically you have it is 0 1 1 0, or even we can have sigma y also, because it has this off diagonal elements are non-zero there. So we, and this, you know, it is basically going to induce transition between the energy levels. So we can, if I, for example, if I in the ground state, if I represent the ground state by say 1 0, or if a state is like this, and if I apply this Pauli matrix sigma x, then we immediately will get that it would become simply 0 1. That means you are going from 1 0 to 0 1 under the application of this Pauli matrix sigma x. That means the transition is going to take place from say ground state to the excited state, or excited state to the ground state, and so on. So therefore this is going to be an interesting Hamiltonian to study here. So we will consider our Hamiltonian to be of this type. Okay, let us proceed further. So I have my Hamiltonian now like this. So I have epsilon sigma z plus h cross omega sigma x cos omega t. So let me tell once again that this h omega is the driving, h cross omega is basically the driving energy, and I can name omega as driving amplitude, and omega is the driving frequency. Okay, so this is what I have. So this is the Hamiltonian. Now we are going to analyze. Okay, first of all, what we'll do, we'll try to solve the so-called Schrodinger equation. So Schrodinger equation I h cross say del psi del t, time dependent Schrodinger equation we have to solve, because we have now a time dependent Hamiltonian. So this is, we have h psi, who is psi is a, this is a column vector. So let us say it has this component like this uv, and then I can write it as I s cross delta t uv is equal to h uv. Okay, these are operators, so please pardon me if I don't put the operator, but you should understand that I'm discussing quantum mechanics. So this Hamiltonian, this is an operator here. Now let us apply this Hamiltonian. I have epsilon sigma z plus h cross omega sigma x cos omega t uv. So what I'm going to get, I will simply get I s cross, I will have del u del t here, del v del t, and you can see that epsilon sigma z, if it is applied there, you will simply get it as epsilon u minus epsilon v, the first term on the right hand side, and the second terms, because sigma x basically takes this, reverse these elements there, so you will get it as h cross omega cos omega t, and here you will get v, and it would be u. Okay, so this is what we'll get. So basically we get two set of equations, two coupled equations we get. And now this equation is basically very it's not analytically solvable, though it looks a very simple equation. These two coupled equation, one you will get from the first row and another one you will get from the second row. These are coupled equations, but because of the presence of this term, this equation is not analytically solvable. So we'll apply a trick here, and this trick is basically say that we'll know more about it later on. So it says let us go into a different variables or go into a rotating frame of reference, because I just want to get rid of this time dependent part ultimately, and we'll see how by a clever trick we can do that. So let us go from this variable uv to some other variable u tilde and v tilde, where I defined my new variable u tilde v tilde like this, and they are connected to all variables uv like this. So u is equal to u tilde e to the power minus I omega t by 2, and v is v tilde e to the power plus I omega t by 2. So I am just changing the variables like this. U I am taking it like, or u tilde is basically u e to the power, or I can say u tilde is equal to u e to the power plus I omega t by 2, or v tilde is equal to v e to the power minus I omega t by 2. Okay, this is the connection between this new variable and the old variable. Now if I do that, and then if I put it in this couple differential equations, then let us see what we are going to get. So let me go by term. First of all, I have I s cross d of dt u v. So I will get, if I just take the time derivative, what I will get is h cross omega by 2, and here I will get u tilde e to the power minus I omega t by 2. You can try to do it yourself. V tilde plus I omega t by 2, and you will also get I h cross. I am now talking about the left hand side of this Schrodinger equation, and here you will get I s cross u tilde time derivative of u tilde, then e I omega t by 2, and this would be v tilde e to the power I omega t by 2. Okay, now going further, so this is the right hand side. What about the left hand side? The left hand side, okay, now I have this, so let me, this is what, so this has to be equal to the left hand side I had, let me just keep it like this, epsilon u minus epsilon v. Okay, u tilde e to the power minus I omega t by 2, and it would be v tilde e to the power plus I omega t by 2. Okay, this is the first term on the left hand side, and you have here h cross omega. You have this cos omega t term, so this I can write it as this cos omega t term, I can write it as e to the power I omega t plus e to the power minus I omega t. Alright, so this is what I will have, and here I have as you can see v and u there, so it would be v tilde e to the power I omega t by 2, and you have u tilde e to the power minus I omega t by 2. Now what we are going to see is that if you just look this both sides, this, okay, and this is your left hand side, and this is your right hand side. You see, left hand side and right hand side, if you compare, only the terms that is having this coefficient, say e to the power minus I omega t by 2 on both sides, or say e to the power plus I omega t by 2 as in the um, column vector in the lower term there, that would become only resonant. Okay, they would become prominent because it would become resonant. But there, if you see from here, okay, I think let me explain it a little bit more properly. If you look at this term, okay, let me just write here. This right hand side, let me write again, epsilon u tilde e to the power minus I omega t by 2 minus epsilon v tilde e to the power plus I omega t by 2. And this term I can write, let me keep h cross omega by 2 here, and then I have in the upper here I have v tilde e to the power 3I omega t by 2, and I will have plus, say, I will have v tilde e to the power minus I omega t by 2. Okay, and in the here in the lower this one I will have u tilde e to the power plus I omega t by 2, and the other term would be plus u tilde e to the power minus 3I omega t by 2. Now you can compare. Okay, let me write the left. If you just look at the left hand side also. Okay, now you can compare left hand side and right hand side. Okay, it's a bit difficult to write everything here, but I hope you will get the point. If you compare both sides, then you see only the term which is having coefficient e to the power minus I omega t by 2 on both sides in the first row, okay, on both left hand side and right hand side, would become resonant. And on the other hand, the terms that is having this, this is going to be out of phase and this would be non-resonant, and in fact this particular term would not be able to contribute much, so therefore we can cancel it. Okay, and similarly here we can, in the second row, we can cancel this particular term which is having 3 omega t by 2, and then this is basically known as the so-called rotating wave approximation. So under this rotating wave approximation, where we have actually cancelled the highly oscillating term like this, 3 omega by 2 and 3 omega by 2, minus 3 omega by 2 and plus 3 omega times 2. This is known as rotating wave approximation, and under rotating wave approximation I can now write my time dependent Schrodinger equation like this in the basis u tilde, in this variable u tilde and v tilde. So this is what I will have. And okay, so let me just write the final equation. You should be able to show that you will going to get this equation. This is what you are going to get: u tilde v tilde plus sigma x h cross omega by 2 u tilde v tilde. So this is the key equations that we obtained. These are coupled differential equations we get under the so-called rotating wave approximation. Now immediately you see that I can now write this in a compact form like this: I h cross u tilde v tilde dot, and this I have a new Hamiltonian now in this new variable u tilde and v tilde, or in this rotating frame, and where h I can express it as epsilon. I will explain it: epsilon tilde dot sigma, where if you look at it, this epsilon tilde vector, okay, this has components like this. You have x component from here, you see x component would be h cross omega by 2. It has no y component, right? It has no y component, it is 0. And z component, you can see from here, it would be simply epsilon minus h cross omega by 2. So what you have seen, that effectively I have now a time dependent problem. I'm now turning it into a kind of a time independent problem by using the so-called rotating wave approximation. Okay, and immediately you see that this block vector sigma, okay, which is now defined for sigma, now defined say for in this new variable u tilde v tilde, uh, precesses freely around this new vector epsilon tilde. Okay, so very cleverly we have obtained or we are able to turn the whole time dependent problem into a kind of time independent problem using this rotating wave approximation and the new variable.
Now let us analyze the problem further and let us see what happens at resonance.
At resonance, the energy gap between the energy level, which is twice epsilon, that becomes equal to h cross omega, or in other words, when epsilon is equal to h cross omega by 2, we are having the condition of resonance. And at the resonance, this epsilon tilde vector would have only the x component. So it would have x component as h cross capital omega by 2, y component is already we taken to be 0, and the z component is going to be 0, because you see, if it is not at resonance, the z component is non-zero, that is epsilon minus s cross small omega by 2. Now at resonance, these are equal, so therefore it would be 0. Okay, and the Hamiltonian would remain as it is. It would be the same form, that would be epsilon tilde dot this Pauli vector here, sigma dot. So as usual, this Pauli vector is going to precess around epsilon, but the precession frequency in this case is easy to work out. Precession frequency, the Pauli vector precesses about this epsilon vector with frequency twice epsilon by h cross mod of that, and because epsilon x component is h cross omega by 2, it has only x component, so therefore you can easily see that this precession frequency would be this capital omega, which is we termed as the driving amplitude, and this has a name, and this is known as the so-called Rabi frequency. This is called Rabi frequency. In fact, what happens is this, say in let me explain it in a diagram. Let us say we have the, okay, first let me draw the coordinates. This is my x, this is my y, and this is my z. So as we now know that my epsilon vector is now epsilon tilde, in fact epsilon tilde vector is now along x direction, so therefore the block vector is going to basically precess around this x-axis. Let us say initially the two-level system is in the ground state, that is it is along the, it is pointing to along the negative z-axis, because you know the Pauli this vector has its component as sigma x, sigma y, sigma z. Now it is directed along z, so it is the, it has only this z component, and if it is directed along the negative z-axis, that is therefore it is in the ground state. Okay, so this is in the ground state. Okay, this is the situation we have. So therefore this and also it is called block vector. So we can plot only the expectation value of sigma, which is we termed as block vector. So this block vector is directed along the negative z-axis initially, and as time goes on, what is going to happen is that this block vector will precede around this x-axis in the yz plane. Okay, and then as time goes on, it will precede in the upward direction. Now at some time, say t, the block vector is along this direction, and so it has traversed an angle, say capital omega t. That is what we'll get after time t. Now if we wait for long enough time, when omega t become equal to pi, then automatically you will see that this means that this block vector will be directed along the positive z-axis. So when omega t is equal to pi, either you wait for long enough time or you can wait for short enough time, but if you increase the Rabi frequency, but whatever it is, if the product becomes omega t is equal to pi, then the two level system will go from south pole basically, or rather I would say will go from ground state to the excited state all right. And omega t is equal to pi when this happens under this kind of a drive, that is known as pi pulse. All right, so effectively speaking, what is happening, I can express these things in this way also. Initially we have started with, say, in the ground state, so this is the probability of getting the two level system in the excited state. So initially the atom is in the ground state, so there is no, all the atoms are in the ground state, so zero probability, right? As time goes on, when say x-axis is omega t, when omega t is equal to pi, the atom will go to the excited state. Okay, now as time goes on, this block vector will rotate it will keep on rotating, and it will rotate along this direction, and finally again it will go to the ground state. So after another pi, that means when omega t is equal to 2 pi, the two level system will again go to the ground state, and this process will go on and on. Of course, in this case we are assuming that there is no dissipation or there is no loss or any kind of things are there, so therefore these oscillations will keep on, and these oscillations are termed as Rabi oscillations. And as you have already I said, this oscillations is taking place at the frequency capital omega, that is the Rabi frequency. So far we discussed the evolution of the two level system, or in other words the block vector with respect to the rotating frame of reference. And there we saw that the block vector rotates about the epsilon vector. The block vector rotates about this epsilon vector with some precession frequency. So this is what we have already seen and discussed. Now the next question one can ask is, what about the evolution of block vector as observed from the left frame? And let us discuss this. This is not very difficult to understand what is going to happen. So basically what we are going to do there, we are going to find out the expectation value of this Pauli vector in the UV basis. that is our original basis. Now we know that uv is related to our new vector, this components u tilde v tilde by this equation e to the power minus I omega t by 2 and e to the power plus I omega t by 2. So because of this, when we calculate the expectation value of sigma Pauli vector in this basis, then we see that this block vector is now going to rotate in the xy plane with an angle omega t. So the block vector will rotate or precess with angle omega t in the xy plane. I will soon explain it actually in a diagram. In the xy plane, in addition, because u tilde v tilde how it rotates we already know in the rotating frame. In addition to the slow precession about the z-axis, in fact this slow precession already we learned there in this example. Here we see that this block vector originally in the downward direction, it rotates in the yz plane about this x-axis or this epsilon vector there, and that is a slow precession. But this small omega here, that is a fast rotation. So overall this whole dynamics in the lab frame will look like this. Suppose we start in the ground state, that means we start from the south pole in the block sphere, and then there would be a very fast rotation in the xy plane, and there be and this is going to, this block vector will go in the upward direction very slowly. It would be a slow precession about the z-axis, and finally it will reach the north pole, and this slow precession is going to take place at the Rabi frequency omega, as we have as we already know. So this is going to be the kind of dynamics of two-level system in lab frame. Okay, now finally let us ask what is the probability to find the two-level system in the excited state, say at a given time t. I mean, can we get a quantitative expression? Qualitatively we already know what we should get, but let us see, or what kind of behavior we get already I discussed it. So again, going back to the working in the rotating frame of reference, I can answer this question easily. Let us see. So this is what my block sphere is. So initially this block vector is say in the ground state. Okay, then it starts rotating, and the question that I want to ask is, what is the probability that it would be found at in the excited state after some time t? Okay, this is what we want to find out. So to do that, I can take the help of this diagram which already we learned in the rotating frame of reference. So after some time t, suppose this is the angle the block vector makes, that is omega t. So we know that this expectation value of sigma z, okay, expectation value of sigma z, if we calculate it in the u tilde v tilde basis, that means okay, psi tilde, say sigma z psi tilde, we can work it out like this. So this would be, say, u star v tilde star sigma z is 1 0 0 minus 1, and then you have u tilde v tilde, and it's very trivial to find out that what you will get is u tilde mod square minus v tilde mod square. So which is basically this is basically the probability of finding the two level system in the excited state, and this would be the probability of finding it in the ground state, because sigma z, you know, these eigenvalues are 1 and minus 1. So this is what we get. Okay, taking this as the hint, now another thing I know, that at any given time the total probability has to be equal to 1. So I can express using this, I can find my P up, that is the probability of finding the system in the excited state, would be, from here I can write it as P up here, that is probability of finding it in the excited state. Using this expression here, I can write it as 1 minus P up here. So therefore it would become 2p up minus 1. So immediately you see p up I can write as half 1 plus expectation value of sigma z. Alright, now if you look at this diagram, we have started, in fact, if you see this diagram, what is sigma z? Sigma z is basically this guy. Sigma z is the projection of block vector. It's basic projection of block vector along the z direction. So as I have started from the ground state, so you can guess that sigma z should be equal to minus cos omega t in this particular case. Okay, because we have started with the ground state, so sigma z at time t is equal to 0 is minus 1. So sigma z should be minus cos omega t. So putting this expression there, so I have P up, probability of finding the system in the excited state would be half 1 minus cos omega t. So you see, we now obtained a very compact equation for probability of finding the system in the excited state at a given time t. So we have got an expression as a function of time, and it is, you know, it is basically dependent on this Rabi frequency, and immediately it's very easy to plot it. And this plot already I talked earlier qualitatively. So if I plot P up, the probability of finding the system in the excited state, and here it's x-axis, say omega t, then we started in the ground state, and then as time goes on, so this kind of oscillatory behavior we are going to get. So this is what I have. This is omega t, and this would say omega t is equal to pi. Then we will get the system in the excited state after pi, then that is, or we termed it as pi pulse. Then after 2 pi, the system will be again in the ground state, and so on. So this oscillation is known as Rabi oscillation.
In this lecture, we have learned most of the fundamentals of a generic two-level system. In the next lecture, we are going to consider a two-level atom interacting with a classical field, and this will give us more insight into the working of two-level atoms and its physics. And this will be very useful later on when we are going to discuss interaction of quantized radiation or quantized light with a two-level system. Thank you.